So hello and welcome to today's webinar from ScyllaDB about designing low latency systems with Rust. I'm Eric, I'm an editor for InfoQ. I focus on Java and security, and almost every system that I've seen follows the pattern of clients running some parts of the application locally, sharing data upstream for things like coordination, device switching, storage, or pretty much every reason that you can think of. And when information goes from that client, nobody really ever wants to wait. So with the aim of not waiting, I'll try to make this a low latency introduction and get straight to an expert at low latency systems and Rust development to talk through the aspects of his designs. And it's hard to top that cool ScyllaDB monster over there, but we'll all try to focus on the content and not get too distracted. So Philippe, take it away.
Thank you so much, Eric. And I think I was just made aware that you were formerly that you work mostly with Java. Hopefully, I won't offend you. On this talk, we are talking about Rust today, not Java. But yeah, I think both languages are actually awesome. So thanks again, Eric, for the very warm introductions. And hi, everyone. I'm very glad to be here, and actually very happy to see that many of you actually have some interest in learning more about Rust. So as Eric pretty much already introduced me, let's quickly go through this slide so we can jump into the content faster. My name is Felipe and I love puppies. Hopefully my puppy won't bark anytime soon. I am also one of the co-authors for a book called Database Performance at Scale, which is basically a free publication which we folks here from ScyllaDB published during my work here at Scylla. And you may want to check it out. I don't know, particularly, primarily because the content today is centered around designing low latency and high throughput applications. So I work as a technical director at ScyllaDB, and in case you are not familiar with it yet, we are basically the database for organizations requiring predictable performance at scale. How do we do that? So basically, ScyllaDB has this close to the metal design that is basically geared towards squeezing every possible ounce of performance out of modern infrastructure. And this basically translates to predictable low latencies, high throughputs, and ultimately infrastructure savings compared to other databases. We are available both as a managed cloud and as enterprise offerings. And since we are a NoSQL database, we also provide full compatibility with both the Apache Cassandra and Amazon DynamoDB APIs. In fact, if people, one of the things people look into Scylla is when they want to run their Amazon DynamoDB workloads outside of AWS. We basically enable you to do that. So here's a short list of logos currently using ScyllaDB to support their data-intensive workloads. Many organizations are here. I just want to highlight here one at the bottom, Discord. Discord is a great example of a company using ScyllaDB and Rust heavily as part of their backend to support their users' real-time messaging experience. Discord previously blogged about their why they decided to switch from Golang to Rust and how they use Rust on top of ScyllaDB. So you probably may want to check out some of their blogs after this talk in case you are interested in hearing about more. All right, so let's take a quick look over our agenda items first. Let's start with some background over why we are here today. After all, what makes Rust so special, right? Why we are not talking today about Java, Golang, or another language? Why is it Rust? Let's understand what is Tokio. And I also want to make a parallel here about the relationship, some of the commonalities that Rust, Tokio, and ScyllaDB have in common. Next, we will do a quick app walkthrough to understand what we'll be covering today. And of course, just like most applications out there, our app will need to connect to a database. And so unsurprisingly, since I work for ScyllaDB, we are going to work with the ScyllaDB Rust driver to connect to a database and then run queries on top of it. And lastly, of course, we are going to run the app, and as time permits, we are going to do more fun stuff. All right. So this is not necessarily mandatory, but I added here a slide in case you want to follow along. And the main reason is because developers like trying things out on their own rather than simply staring at a screen share. And because we are basically using Docker here, it might take some time for you to pull and build the necessary container images so you can get an environment up and running. All right. So those are the basic instructions. You can check out the README there in this GitHub repo, so you can understand how you can get things set up. But otherwise, it's basically run those 3 commands here and off you go. All right. All right. So at this point, I really want to take a step back and provide you some context over the initial question I posed. Why Rust? After all, it is definitely a programming language that has gained lots of popularity and attention recently. And one of the reasons for that is primarily due to its high performance and efficient use of system resources. Rust makes it really easier for developers to, build highly concurrent asynchronous application with a special focus on memory safety, which is really the dream of most software engineers out there. In particular, when you are coding in Rust, you don't have to worry about things like, garbage collection pauses, null pointer exceptions, and null pointer references, memory leaks, and other things that somehow might affect other programming languages. Those are things that really differentiate Rust compared to other languages. It's safety. If you are starting your Rust journey, one of the things that I would highly recommend you, one of the materials I would highly encourage you to take a look on would be the official Rust book and start building up from there. And the main reason is because you are eventually going to realize that the path is not hard, but it's also not straightforward. Because Rust is basically this programming language which actually teaches you how to become a better programmer in the long run. When we talk about data-intensive applications, these applications often rely on asynchronous programming to quickly process, lots of data. In the Rust world, this means using the Tokio framework, which facilitates the task of, never blocking while waiting for resources on disk, waiting for tasks that you expect, calls that you expect to receive from the network, and so on. And all these characteristics really make Rust a good fit for saving on infrastructure costs, or making a better use of limited infrastructure, as is the case of embedded devices, for example. So in the Rust world, when we are doing asynchronous programming, we are basically using this framework known as Tokio, which is perhaps the most mature asynchronous framework available in Rust today, used in production by many applications. Of course, Tokio's job is basically facilitating this task of basically doing concurrent asynchronous, highly concurrent asynchronous programming. Another thing is that when you are using Rust, more often than not, you will be using Rust to build scalable backend applications, and inevitably you will need to communicate with third-party services like a database to store and retrieve data as needed. If you are working with a database, this is really where I want to introduce ScyllaDB. Because ScyllaDB really, we are the only database which has this special focus for extremely high throughput and low latency applications. Compared to Rust Tokio, which is the asynchronous framework I previously mentioned, in ScyllaDB, we make use of a framework which we call a Seastar, which is basically an asynchronous C++ runtime which follows a polling architecture. As your Rust application places a request, this request will eventually land to ScyllaDB, and then there will be a busy loop which will submit this request for processing, and after they are complete, we simply submit the response back to the caller. So this is basically how ScyllaDB works internally. Talking briefly more, a bit deeper about ScyllaDB real quick, and then we are going to start talking about Rust. So although ScyllaDB uses Seastar, it's worth mentioning that it's not only ScyllaDB that really uses this framework. There are other projects out there making use of it, such as Red Panda and also the Ceph distributed storage system. All those to make use of Seastar. Um, and so what makes really Seastar different from Rust, Tokio, and other asynchronous frameworks? There are basically two main things. First, Seastar basically implements a concept which we call a shard per core architecture. And shard per core means that incoming work gets sharded on a per CPU basis. And every CPU runs its own dedicated reactor loop. What this means is that the architecture pretty much also follows a shard knotting model, because each CPU is basically perceived as an individual entity. We also shard the other computing resources available in a server on a per CPU basis, such as memory, disk I/O, and so on. And one of the benefits of doing that is that basically we have no context switches. And this is important because context switching can be really detrimental to application performance, especially databases. Furthermore, cross-CPU communication and synchronization do not really rely on any locking primitives in ScyllaDB. So for example, if we need to retrieve data from a remote CPU, all we do is simply synchronous message passing. We send a message for that CPU, hey, I want that data, and when that data is ready, we get it back. That's it, no locking, no need for complex locking primitives whatsoever. And the second aspect about Seastar that differentiates it with Rust Tokio really drills down to what we call as user space schedulers. So data-intensive applications, as the name suggests, they can be really intensive. And due to that, it is important that the database efficiently makes use of our available I/O resources to maximize the server utilization, while also being able to carry out other background tasks. Because databases, it's not just about writing data and reading data. They have to, in the background, they needed to run other operations. So the Seastar I/O scheduler basically abstracts that away from programmers and dynamically tune tasks priorities as basically the workload conditions vary over time. Another thing, another really nice aspect about our user space I/O scheduler is that we basically provide all the goodies as available in asynchronous and the direct I/O for basically disk I/O. So we are basically able to maximize your storage utilization at all times. So this is basically how ScyllaDB can get to very efficient hardware utilization while sustaining single-digit millisecond latencies. And also thanks to that shard per core model I previously explained, performance basically linearly scales. So for example, if you connect your Rust application to ScyllaDB and you say, yeah, basically my cluster seems to be a bit overloaded, you basically double the cluster size and you get double the performance, which is super cool because it ensures that your infrastructure spans are always in check. All right, so this is the quick intro about Rust. And this basically brings us to the first poll that we've prepared for you today. I want to know how proficient are you guys currently with Rust? There's one option here which is called like Felipe, I'm learning, and I believe pretty much that's where I would that's the one I would answer, because I believe life is always a learning curve. And I mean, please take some time to select to answer the poll. And with that, thank you so much for your responses. And just so you guys know, the winner here it's on my list to learn. And the second placed one was like Felipe, I'm learning. So yeah, let's learn some things new together. All right, so with that, let's discuss the simple app we are going to walk through today. And the app is basically a three-part component where we first ingest some data to ScyllaDB. It deploys our initial schema, and it's basically going to simulate an IoT application, generating measurements for a while, basically 3 days. Next, the second program is called Metric Reader. It's basically an aggregator. And what it does is it will scan through all the data we ingested and allow us to run analytic queries, like in order to know things like how many measurements each device recorded in the previous exercise. And lastly, our third and final program is arguably the most straightforward. It demonstrates how to run simple point queries and retrieve a specific maximum, average, minimum aggregates over a range of time for a specific device. All right, so naturally, because our Rust application will communicate with an external resource, we need a driver to be able to abstract all the underlying complexity of the protocol. And this is another area where ScyllaDB particularly shines. We are one of the few database vendors out there that actually ships native Rust implementation. And what's the performance difference of implementing things in Rust other than so basically having a native Rust implementation definitely makes a difference. I previously mentioned that ScyllaDB is compatible with Apache Cassandra. So what we did was to compare the performance of our driver versus the GoSQL driver, which is the one in Go, as well as the Cassandra Rust driver, which despite its name, isn't really a native implementation, and instead it relies on the C++ driver API to translate syscalls and converts types from Rust to C, so it adds lots of overhead. And as we can see here in the results on this table, our native implementation is around 3 times faster than GoSQL, where the C++ bindings from Cassandra are simply just too slow. So here's another cool thing about using Rust in order to develop your code. Rust bindings basically allow you to easily reuse and share a given library feature in Rust and reuse that code in other languages. This is done via foreign functional interfaces, as available in pretty much most major programming languages. And this is exactly what we've done with our C++ Rust driver implementation. So this basically allows you to benefit from our Rust driver performance when coding C++. And likewise, other community members created this product, which they called ScyllaPy, which does the same, but for the Python language. And of course, the benefits here are enormous. We no longer need to maintain separate driver implementations on a per language basis. And because the Rust driver is basically the parent driver and is used under the hood of all those implementations, shipping new features or fixing bugs automatically get extended to those children implementations. Therefore, I definitely look forward to a foreseeable future when you are using Rust without even knowing it. All right, so we already know that we want the Scylla driver because I said many times that our app is going to connect with a ScyllaDB database. And likewise, in your real life, you may be after a given library that already exists. So how do we go about it? If this is your first time hearing about Rust or playing with it, in the right-hand side, there's a picture of this website called crates.io, which is like a PyPy for Python programmers or npm.js if you're a Node.js programmer, for you to easily find and learn how to use specifically libraries in your code. In our example, we are showing the Scylla crate, which is the ScyllaDB driver, which is and a crate is basically analogous to a library or a project in the Rust vernacular. Crates in Rust or libraries also come with a concept known as features. And by default, features are additive. Thus, features, they basically add functionality to a given, to an existing library functionality. For example, in the example shown here in this slide, we can see that the Scylla crate has an SSL feature for enabling encryption in transit. We have another feature called Cloud to be enabled when you would want to connect to our ScyllaDB Cloud managed offering. And we also have serialization specific features to handle, Rust to database type conversions, because Rust has a specific set of types. The database understands other set of types. How do they talk about how do we make those two communicate? So those are the features which basically make all the magic happen. And one of the cool things about features is that you don't need is that basically features help with reducing binary bloat when you don't need them. And this, of course, enables faster compile times, smaller binaries, which in turn are really good to save on disk space and somewhat also on performance when it's a concern for your deployment. All right. So all that said, let's quickly jump to our code. And I do have my screen share here. I have a code, but first I want to get to my terminal. Do let me know in case you guys want me to zoom in my font. I am trying to pay attention to the chat. And guys, just as a heads up, this terminal I'm using, it's written in Rust. It's called Ghosty. In case you guys want to check it out, it's super fast. If you guys don't believe how Rust can be fast, just download Ghosty and compare how long it takes for you to cat a very long blob file. Either way, so here's our application. In order to save us time, I already spun it up using Docker Compose. And in case you guys are following along, what you want to do before you get started with it is really check the logs of the Rust app container. And once you guys see this message saying that ScyllaDB is up and available, it means your database is up and available, which means that we are ready to go. So the first thing I'm going to do really is connect to our Rust application. And we are going to run the first program. And here, of course, I am copying and pasting. No shame about that. But what we are doing here really is cargo run. So we want to run a program, binary, which after the program gets compiled, it becomes a binary. We want to run this binary called metric collector. Here are the arguments we are going to basically send to specify to this program. And it looks like I copied more than needed. Yeah. And let's remember what this program does. It creates our resources and populates data to our database. So basically now it's connected. It's creating key space and creating tables. And also that's done, boom, just like that, 86,000 queries have been run. And one of the things I want to call out here, because I mentioned that ScyllaDB is really nice for data-intensive workloads. All of this is, of course, running on my own laptop. So latency could go a bit south, but in this case, it was actually nice. But we can see here the average latency of each individual request was 13 milliseconds. The P99.9 latency was 28 milliseconds. Of course, in a real production environment, that would probably be single-digit milliseconds. That's really the performance that ScyllaDB promises. All right. So all that said, let's really see what this program does. And here it is, metric collector. If you guys visited my GitHub, you probably realized that each program is basically a single very big file. And there is a reason for that. The reason is because, when we are following code, demonstrating code in a single file is much easier and much more intuitive than, having a project with where you split database resource and structs and libraries and things like that. So here is everything's a single file. It's really easy for us to reason about. All right. So here's how Rust works. Just like with other programming languages, we import basically all the resources we are going to be using in our program. And then we, at the beginning, we specify a few constants, which basically determine how much data we are going to ingest as part of the program execution. And I want to call out here for this parallel constant, which is really, it says concurrency, but it's actually parallelism. It's wrong, sorry. And the parallelism basically indicates how many queries we are going to send in parallel against our database. And we are going to see how this is actually used when we get to see Tokio actually in action here in the code. We already saw it in action. All right, so what comes after? We basically parse all the arguments that we submitted in the command line, nothing specific here. And then we basically connect to our cluster. We specify the key space and tables that we are going to create, and then we initiate cluster connection. One of the cool things that I really like about the Rust driver, at least our implementation, is this concept of profiles, which basically allow you to, create different connection parameters with different criteria, such as timeout settings, things like that, so that you can reuse it during the lifetime of your application. And why is this important? Sometimes you may have a multi-region deployment where some queries needed to be routed to, I don't know, Europe, other queries need to be routed to the US, and you want to easily switch among those, or sometimes some queries may be really expensive to run, particularly when we are doing full scans. So profiles really make it convenient for you to switch from one to another in a super easy way. And then after we specify everything, this is really the piece where we specify our session, and we configure compression, we configure authentication, pretty much what you would expect from any other driver connecting to any other database. And then we connect to ScyllaDB, and then we get to this piece where we actually start creating our resources. After our resources are created, we start basically, we basically prepare our insert statement. And prepare statements are really something that, if you're not familiar with them, you should be, because prepare statements are great for performance, because they basically allow, they prevent the database from actually needing to parse your queries every single time as they come in. And they also prevent, they are also great for security, because they prevent things like SQL injection, right? So I previously mentioned that ScyllaDB is a distributed database. So one cool thing about ScyllaDB is that, you have this concept known as tunable consistency, which is nice. So for example, if you're running an application where you can tolerate some stale reads, you can lower the consistency for higher performance. Whereas if you need more strong consistency guarantees, you would typically want at least local quorum consistency. If you are familiar with Apache Cassandra, it's basically the very same concept. All right, and those are basically the basics. So remember, we connected to the cluster, created the resources, we now configured our statement. What's next? Basically, let's blast that cluster with some data. So what we do here is basically we create a number of semaphores so that we can somehow limit their parallelism on the client side, given that constant that I previously highlighted earlier. We then specify how many devices we want. I want 100. And what we do next is basically we iterate through all those devices. And what we do is during this iteration, we basically spawn a Tokio task. There it is. It's basically an asynchronous task, which is going to effectively execute our insert statement. All right. And because we are using semaphores in order to limit how many requests are going to be sent in parallel, we basically, each semaphore basically holds a permit. And as soon as that request completes, that permit is released, and another request may come in and take place in that semaphore. It's like a ticketing, right? It's a semaphore after all. And once that's done, because everything we are doing here is asynchronous via Tokio, we basically have to wait for our in-flight requests to finish, otherwise you lose data. And once our requests in flight are done, we basically print the final metrics as we have seen on the screen. And this is super cool because not all database drivers out there actually print metrics like, hey, this was your P99, this was your average, this is how many errors occurred during your execution, etc. and so forth. This is really something unique about our Rust driver. And it makes it also very easy for you to bundle it in your application. So in case you want to, expose it throughout Prometheus endpoint or something like that. All right. So this is the first program, and what I want to do now next is, of course, let's run the second one. And the second one is a bit more complicated. Because remember, guys, I previously mentioned that ScyllaDB is actually a NoSQL database. And being a NoSQL database, we are actually a wide column NoSQL database. It means that we do not support regular querying like, joins, locks, locking at transactions to multiple keys or anything like that. But sometimes you may want to run queries like, hey, I want to know which device in the past week reported the most, the highest temperature, or the top 10 temperature over all my devices. Those are types of queries that are not necessarily easy executable on a database like ScyllaDB. The ScyllaDB is basically a database primarily geared towards really point queries when you need to retrieve data fast and you ingest the data in the same way as you read it. And so, okay, what we did here, basically we ran what we call a full table scan, an efficient full table scan in Scylla. And this efficient full table scan basically running a divide and conquer approach. And for every device it found, it reported how many rows it basically had. And then at the end, it reports the latencies. And here you can see, basically, we've run 18,000 queries, and the P99.9 latency was 4 milliseconds. That's impressive, right? So as you guys can see, it took an infinite amount of time for me to explain than just then it takes for the program to actually run. So let's take a look into it. And I'm not going to walk through everything that we already saw. So the main difference here is that a full table scan is basically a divide and conquer approach. So distributed databases basically work, as a distributed hashing table, where each node is basically placed into a ring, and each node in your distributed cluster basically owns a portion of your data. And with consistent hashing, basically we end up with a ring, which we call as the token ring. And what we do basically is we get this ring and we split it into small chunks, very small, smaller chunks, which is basically the end formula, which is here. And those smaller chunks are then the queries we are going to blast against the database. And also we traverse the entire ring. Done. We've finished running a full table scan. That's the difference. In case you're not familiar with it, this may seem complicated, but it's not really. Basically, as you guys can see, it's like a 10 lines of code, something like that. So yeah, it's super straightforward once you get to it. But there are some solutions which actually automate this to you. So for example, Apache Spark. When you connect Apache Spark to a database, any database, basically this divide and conquer approach, which I'm basically implementing here as code, is exactly what tools like Apache Spark or Presto are going to do. All right. So this is what really the second program does, and it shows how you can actually accomplish that very efficiently in Rust with ScyllaDB. All right. Let's go to the third and final program and then wrap up. So the third program is actually the most straightforward. It's basically the one we run when we want to retrieve data for a specific device. So I want to retrieve data from this device, and I want data only from January 1st until 11 p.m. And then it's going to retrieve me the minimum, maximum, average that this device basically recorded. And yeah, that's it. Basically, pretty much all the values here are random, so don't exercise too much attention to it. And this is really what this code here does. And if we look into the code, really, it's very straightforward. But one cool thing about this program I want to highlight is every now and then, when you are working with a given programming language and databases, you will need to do work with timestamps, dates at time, things like that. So this code is really nice because it shows you, hey, how can I convert from a user supplied timestamp and convert it to UTC, or convert it to local time, or convert it to RFC 3339 or things like that. So those are things that we really needed to learn about our way with Rust. And really, here we are demonstrating how to do that. And then more towards the end of the program, we ran one query per each function. We do not need to do that. We could run a single query running all aggregations. And this is also shows that, of course, ScyllaDB runs supports aggregations just like any other regular database would do. All right. So this is really the quick walkthrough about Rust and how it does. I haven't shown too much about performance, but in case you are curious, I'm currently working on this. Yeah, I don't. I'm currently working on this Blue Sky Firehose consumer, which basically gets data from all activities running the Blue Sky network, which is a like a Twitter-like microblogging social network. And all the data I am ingesting to ScyllaDB, like for example here. And if I run this, I mean, you guys are really going to see how fast this can be. So yeah, now as you guys can see, a bunch of stuff is happening here on my screen, which I think it's super cool. So for example, you can see things like, hey, someone posted something on Blue Sky, and here's a like event, someone liked a post, and things like that. All right. So this is pretty much what I wanted to show. If you are interested in learning about Rust, or in case you answer that you are already using Rust as in production, you may want to check out our P99Conf conference at p99conf.io. Last year, we had talks from Carl Lurch, principal engineer in AWS, basically the inventor of the Tokio asynchronous framework. And he also, he basically spoke about Rust, a productive language for writing database applications. We also had Amos Wenger speaking about Rust, IO, URing, KTLS, cool stuff, and tons of other content related to Rust. If you are interested in high performance, extreme scale engineering, I also want to invite you to Monster Scale Summit. This is a conference hosted by us here at ScyllaDB, and we are going to have companies from Disney Plus, Discord, Visa, Uber, Rust from the Rust community, and many others also talking about how they are tackling their most hard and scary engineering challenges. All right. So all that said, this is what I had to present, and I'm happy to take your questions. Eric, I hope I have not overrun my speaking slot.
Nope, you are in good shape.
Awesome.
So anyone who was paying attention, there was the typical question, which I forgot to address in the intro of, are we sharing the recording link for this webinar? Yes, the recording link will go out soon, along with a copy of the presentation. Those things will show up in your inbox after a little bit. But if anyone else wants to ask a question, feel free, either type it, there's a question box over in the right, or hit the chat down there. But in the meantime, let's look at the couple questions that came in. The first question is, what are the different consistency types for Scylla?
Ah, very good. So there are many different consistency levels, that's how we call it, that we support. One is basically 1, which means that request, in order to be considered successful, needs to be acknowledged by a single replica only, and then done. It responds back to your application. A quorum means a majority. So if you have, for example, a cluster with 3 nodes and you are replicating your data 3 times, then a quorum is 2, because it's half 3 plus 1. And then there is all, which is basically all replicas involved for typical requests. There are more consistency levels, but those are generally the most used ones.
All right, cool. Another question came in here that says, what are the most common use cases for Scylla? And one of your colleagues in the chat has a link of ScyllaDB.com/fit, which might explain like a way that a couple people use it and different customers use it. So from your perspective, what are the common use cases?
That's a really good question. I kind of floated some ideas here already in this webinar. So for example, IoT is definitely a great one. Discord, remember when I mentioned about Discord? Discord actually uses ScyllaDB heavily as part of their real-time communications. The sample application I showed about Blue Sky, this is not a coincidence. I haven't picked up Blue Sky at random. Blue Sky is using ScyllaDB under the hood to service most of their microblogging traffic. EA Games, Epic Games are companies who are using ScyllaDB in the gaming industry. Another TripAdvisor is using us for machine learning and recommendations. So imagine when you visit the TripAdvisor website, they quickly need to know who you are in order to provide you recommendations. So hey, have you checked out this hotel? Or hey, I see you are going to travel to Lisbon in Portugal. So what about this trip? Is this interesting to you? So basically, ScyllaDB is behind the scenes servicing that for TripAdvisor. So plenty of use cases.
Got it. So one of the other questions, how does ScyllaDB work with serverless applications? And I think specifically they're talking about is the backend itself serverless, or does a ScyllaDB need to consistently run?
Good question. So ScyllaDB, the backend needs to consistently run. We are not a serverless offering, at least yet. But there's also the other side of this question as well. I mean, if you have a serverless app and you want to connect it to Scylla, of course it works. One thing I would recommend you not to do would be to frequently be spawning too many applications, because this can create lots of connections against your database. TCP connections, establishing network connections in general is a very expensive process for any application out there. So you typically want to have, a constant connection flow from your application to your database. Or you can also place a Kafka in the middle where, there's a sink, you can Kafka connect, and then it syncs to ScyllaDB. But yeah, we are not a serverless just yet.
Can you go in a little more to the role of when you would or wouldn't put Kafka in the middle? Like if I have a variety of clients, like you talked about Discord and the common case, Discord has a lot of clients who are logged in on web browsers and phones. So how would they make the decision of when they want the client to connect directly to Scylla, which is what your Rust driver did, versus when you'd want a Kafka or a broker in the middle?
Right. Yeah, in general, you typically do not want to let the user directly connect to your database. So for example, when I was showing the code sample, I showed that constant called parallel, which was basically to limit the parallelism of requests we would be sending to the database. Instead of doing that approach and doing a semaphore in code, instead we could simply put our request to a Kafka queue, and then from there we would simply consume from it from the backend side. And one of the upsides of following that architecture is that, for example, if your database goes down, or if you have an error in order to when you're trying to write a given record, then you don't lose the data, right? So that's definitely we want to use brokers and queues in your data flow. There's no way around it. also because you want to safeguard your users that their data is not lost, right? In case it fails for whatever reason, in case there's an exception, whatever. Another cool thing about following this queuing approach is that, a really nice thing about Kafka that I like is that concept known as offsets, where if something bad happens, I don't know, you lose your data, or someone, a bad admin goes and truncate all the data on your table, you can simply go back to the first offset and replay everything that all transactions that happened ever since. This is super nice.
Got it. So that offers a form of resiliency. So if you need to replay information from the broker and something happened on the database, you can just go and reprocess it again.
Exactly.
All right. Are there any approaches where people who use ScyllaDB or write a Rust application, like, have you found any particular good practices of, I follow this on a consistent basis and therefore things work out well?
So in general, using structs in Rust is a really, in general, structs in Rust are really nicely implemented, contrary to other languages. And I think the best practice is when you are basically working with a database, databases have a schema, and managing a schema from code, it's always tricky, because sometimes your database schema changes, but you forgot to update your code, and then everything breaks. In Rust, and particularly also when you are coding for Scylla, I highly encourage you to make use of structs when you are basically inserting your data. I haven't used that in those examples because I wanted them to be straightforward. But in our examples in the Rust driver documentation, we actually show how you can do that. Because then if your database schema changes and your struct is not, your database and the driver does not understand the translation of your application schema with the database, it will warn you back, and then you can say, oh, something weird happened here. Yeah.
Yeah, I've seen a lot of companies where they start off really quick and they have schema-less exchanges, and they just exchange information, and you can get going really, really fast. It's really easy to develop. But after a brief time of that, the role of, we need to lock down schemas, we need to actually define what the items are supposed to be. I'm a big proponent of static typing.
Yeah, me too. I love it as well. Yeah, DynamoDB it does not follow that, and many users get confused. Yeah.
I was trying to keep my opinions about DynamoDB to myself now, but you kind of picked up on something that I don't particularly like about it. But yeah, so it seems like you have kind of native object binding for Scylla that makes it easy to code with fully defined contracts. Is that right?
Exactly. Mm-hmm.
All right, and then I assume Rust has way of enforcing those types. What about situations where people do need more dynamic typing of objects? Like, how do you handle those situations where you need a dynamic field or two?
Good question. So ScyllaDB supports one concept which we know as, we call it as user-defined types. So basically, what's an user-defined type? It's whatever you want. So for example, one example, in that blue sky example I ran, when a user is going to post something on their social network, they can post a variety of stuff. They can post a YouTube link, they can post a website, they can post, they can upload an image, they can upload a video, they can do things like that. And if we analyze alone just the image part, for example, an image has what? An image has an aspect ratio. An image needs to be stored somewhere. It has a metadata. It has a type. It might be JPEG. It might be PNG. It might be whatever, bitmap. And user-defined types really allow you to specify those contracts that you have in your application. They are also extensible. So if UDT changes, if the type needs to be updated in the future, you can easily go and add a new field to it. And you can also make nested types. So for example, when you are embedding something into a post, you can embed a vector of images and or a vector of images and videos, and you can also post links to it. So yeah, it needs to be dynamic, support just the dynamic environment as it is for most applications out there. So UDTs, user-defined types, are really the kind of type you would want to use for that.
All right. If anyone else has additional questions, I think we got to the majority of ones that came in terms of the questions that I see. But if you still have something you'd like to ask, please feel free to do that. But to expand a little bit more about what you're talking about with user-defined types on the backend database, it seems like if you have a nested JSON object or a nested object, you can query a little deeper in an object versus needing like join tables with your typical relational database.
Right. You can retrieve the entire object at once. Querying it is a bit more complicated. For example, if you are trying to use a UDT to basically reproduce a schema representation, and you are trying to search through those JSON representation, just like you would do with MongoDB, then we are not necessarily a good fit for that. We are not a document database. We are a wide column database. Yeah.
Okay. What exactly is the difference between a JSON database and a wide column database?
So in a document database, as we just spoke, they basically store documents, right? And they basically allows just kind of query you just mentioned. You can search within several document. In MongoDB, they call search within a collection, right? And you can even run more complex queries and even nested searches. The problem is that running these sort of searches, they are quite expensive. Whereas on a wide column, basically you have a key, and under that key, this key is clustered in rows. So for example, typically you would have posts by a user. So you have the user ID, and then you have a clustering component, which is your timestamp, and then you would be able to scan throughout all the posts of a given user on via a timestamp basis. And this allows you to run really point queries where you need the data fast. So give me all the posts from this user because someone is viewing their profile. And this is super quick, contrary to searches. Yeah, that's the difference really.
Got it. All right, so I'm looking through the chat here, Rust driver example and the repo link. So it's nice that people who want to use the Rust driver can just go and pick it up. ScyllaDB, oh, that's the Python driver there, C++ driver. The only thing I don't see here is a Java driver.
Well, maybe we are waiting for you to implement it, right?
Oh, you guys don't have one? Okay.
No, we don't have a Java driver. We don't have a Java which uses the Rust bindings for so that we can use our Rust driver instead of supporting a totally separate project just in Java. But we do have a Java driver, yeah.
Yeah. Okay. Cool. I kind of figured it would be there. All right. Any kind of parting words? We're at 55 after. So if somebody's interested in either following the Rust project or picking up some information on Scylla, what's some final information that you have?
So basically, if you guys want to learn more about Scylla, I brought this slide for us. So visit our website. It's ScyllaDB.com. In case you want to ask point questions about Scylla, we have two resources for you. Slack.scylladb.com is basically our Slack. And we also have our community forum at forum.scylladb.com. Also check out our social media. Events like this, we always stream it there, GitHub, and so on.
Sounds good. All right. Thank you very much, everybody, for attending.
Thanks, guys.
Great
See you
day.
next time. Bye.